In this video, we will be discussing acid-base titrations, particularly what the acid-base titration curve looks like for both a strong acid, strong base, and a weak acid, strong base titration. We will also be looking at polyprotic acids and pH indicators. A titration is the process by which we determine the concentration of an analyte, that is our component that we will find in the flask, using a titrant, the component that will be in the burette. So there's a variety of different types of acid-base titrations that one could do. A strong acid, strong base, strong acid, weak acid, strong base, being either monoprotic or polyprotic. A weak base, strong acid, again, mono or polyprotic weak acids. The terminology here has a particular order to it. The very first term refers to what will be the analyte, or the thing in the flask, and the second term, in this case strong base, is the thing that is in the burette, the titrant. Now, we'll be talking about some of the key points on a titration curve. There's the starting point, which is the very first location, or the pH when you start, before you've added in any of the titrant into your analyte. The buffer region is a particular region where the pH curve is flat, and there's a particular type of calculation that we can use to determine the pH in that region. A key place is the half equivalence point. That is the location where you are halfway towards the equivalence point of a titration. We'll talk about the key values that you can get from the half equivalence point. And then we'll talk about the difference between endpoint and equivalence point. And then equivalence point as it relates to first, second, third equivalence points for polyprotic acids. So the first titration we're going to talk about is a strong acid, strong base. Now, going back to our earlier discussion on strong acids, a strong acid is one in which the acid itself fully disassociates so that the concentration of your H+ is equal to the concentration listed for the acid. So for example, if we said that we were working with a 0.1 molar hydrochloric acid solution, then the concentration of the hydronium ions, the H+, would be 0.1 molar. All the hydrochloric acid would disassociate into H+ and Cl-. The strong base, because it's, again, strong, it also fully disassociates. The most common strong base that is used in a titration is sodium hydroxide. So if we're talking about a strong acid, strong base titration, that means that our strong acid is down here in the flask, and the strong base is up here in the burette. So while we are doing a titration, as we're continually adding sodium hydroxide, in this case, to hydrochloric acid, the pH is going to be changing. The reason that it changes is because the sodium hydroxide is neutralizing the hydrochloric acid. We also have another thing that is causing a change in the pH, and that's dilution. So there's two components when we're calculating values on a strong acid, strong base titration that we have to keep in mind. The first is neutralization, where the acid, in this case, is reacting with the base, and dilution. We are increasing the volume down here, and because we're increasing the volume down here, we are affecting the concentration of the hydrochloric acid through dilution. For strong acid, strong base titrations, the autoionization of water is generally only important near the equivalence point, and the equivalence point for a strong acid, strong base, or even a strong base, strong acid titration is going to be pH 7. The equivalence point is the location on a titration curve where you have added the same number of moles of base as you had acid, or acid as you had base, depending on the type of titration you're doing. In the case of a strong acid, strong base, or strong base, strong acid titration, because what you're doing is completely neutralizing the acid or base, there is no acid or base left over, and so the equivalence point for these is going to be pH 7, essentially the hydronium ions that come from water alone. A more complicated titration is a weak acid, strong base titration. For a weak acid, they don't fully disassociate. They establish a dynamic equilibrium at any point along the curve. So because they don't fully disassociate, as you do the titration, you're going to have some of the acid that's still in the acidic form as HA, and some that has disassociated into the H plus and A minus. So when we're adding the sodium hydroxide, the titrant from the burette, it will be neutralizing the hydronium ions that are in solution, and that will be in effect removing some of our product, causing some of the remaining HA to break apart, just according to the Le Chatelier's principle. For the strong base still fully disassociates. So the number of moles that we're adding from the burette is the number of moles of acid, or H+, that are going to be neutralized during the titration. Just like when we were talking about a strong acid, strong base titration, there's two things that we need to take into account when trying to figure out the pH along a titration curve for a weak acid, strong base, or a weak base, strong acid titration. We have the neutralization, the acid reacting with the base that we're adding in, and we have dilution. Because we're adding liquid into our acid solution, in the case of a weak acid, strong base titration, the concentration is going down just because of the increase in volume. For a weak acid, strong base, the autoionization of water is important as we get close to the equivalence point, where the concentrations of the H+ coming from the acid solution are fairly low. The equivalence point for a weak acid, strong base titration is not going to be 7 as it was with the strong acid, strong base titration. What you will find is that for a weak acid, strong base titration, the equivalence point, the location where the curve is the steepest, about there, that is the location where you've added the same number of moles of base as you had acid. Now, because some of the acid doesn't fully disassociate, you actually have an excess of hydroxide ions compared to the hydronium ions. So because there's an excess of OH, the solution will be slightly basic at the equivalence point, meaning that the pH of the equivalence point for a weak acid, strong base will be greater than 7. Now, some of the key points on a titration curve. We have the starting point. That's the point in which you start where you have not added any of your titrant, the thing in the burette, into solution. We have the end point. Now, the end point is more of a location where you would use a colorimetric or a pH indicator, and the end point is when you stop the titration. The equivalence point is what you're trying to get or approximate by the end point, and that's the location where you've added the exact same number of moles of base as you had acid. Again, the end point is not necessarily the equivalence point. The end point is where you stop doing your titration. Typically for a colorimetric titration, you select an indicator that gets you as close to the equivalence point as you can get. But the equivalence point is not necessarily the end point. The half equivalence point is halfway to the equivalence point. The half equivalence point is when you've added half the volume needed to reach the equivalence point, i.e. you have added half the number of moles of base as you had acid. The reason that this is important is at this location, using the Henderson-Hasselbalch equation, we will find that the pH is equal to the pKa. So if we're doing one of these titrations using a pH meter and we determine the volume of the equivalence point, we can find the half equivalence point by going half that volume. So for example, in this diagram here, our equivalence point is at about 20 milliliters. So the half equivalence point would be at 10 milliliters, right? So at this location, our pH is equal to our pKa. Then there is the buffer region, which is the level but slightly increasing section of the titration curve where it's level through this region. This is the region where the Henderson-Hasselbalch equation is valid. Essentially, it's where the concentration of our acid and conjugate base, not the base that we're adding, but the conjugate base, has a 1 to 10 all the way up to a 10 to 1 ratio. So at the very beginning, you have 10 times as much of the acid as the conjugate base. At the end of the buffer region, you have 10 times as much conjugate base as you have acid in solution. Another complicating factor is when we have acids that have more than one acidic proton, our so-called polyprotic acids. We can do a similar titration with polyprotic acids. What you'll find is that as you do a titration, each one of the hydrogens will come off sequentially. So if we have something like H3PO4, what you'll find is that one of the hydrogens, the first hydrogen, will come off of all of your H3PO4s to make H2PO4-. Once all the first hydrogens from H3PO4 have come off and your acid is completely in the H2PO4 form, only then will the second set of hydrogens start coming off. Each one of your locations on your titration curve, each one of the different hydrogens has its own pKa value. The first acidic hydrogen will be called pKa1, the second acidic hydrogen will be pKa2, and the third acidic hydrogen will be pKa3. You will have 3 different equivalence points. The interesting thing about the equivalence point is because the equivalence point is the location where you've added the exact same number of moles of base as you have acid, each one of the equivalence points will be equidistant, i.e. if it takes, in this case, 50 mils to reach your first equivalence point, then to reach the second one would be an additional 50 milliliters, which would make it 100 mils. And then your last equivalence point, the third hydrogen's equivalence point, would be another 50 mils. Right? So the distance to get to the first equivalence is the same amount of volume as is needed to go from the first equivalence point to the second, and the second to the third. The pH of the half equivalence point for each one of these subsections will be the pKa of that particular acidic hydrogen. So for the first one of H3PO4, the pH is going to equal the pKa at the half equivalence point, so at 25 mils, which represents the first acidic hydrogen coming off. For the second one, you will find that the pH is equal to the pKa2 at the second half equivalence point, which is the midpoint between the first equivalence point and the second equivalence point. And then finally, your third half equivalence point, the location that's halfway between your second equivalence point and your third equivalence point, the pH will be equal to the pKa for the third acidic hydrogen. Now, the way that you're going to figure out the pH at the equivalence point is the pH at the equivalence point, unlike before where we have to do a complex calculation to figure out the equilibrium at that concentration, for your polyprotic acids, the pH at the half equivalence point is actually going to be the average pH between your first and your second half equivalence point. So the equivalence point for your first acidic hydrogen will be the average of the pKa's of your second equivalence point and your first equivalence point. Your second equivalence point will be the average of the pH's or the pKa's of your third half equivalence point and your second half equivalence point. The third equivalence point we have to calculate based on an equilibrium between the phosphate, the PO43- ion, and the hydroxide that you've been adding in. The last thing that we're going to talk about is the selection of acid-base indicators. Now, sometimes you're not going to have access to a pH meter, or you just want to do a quick titration to get a good approximate idea of the concentration of your analyte. In order to be able to do that, you need to know the approximate pH of your equivalence point, and then you will select an acid-base indicator. An acid-base indicator are themselves acids and bases that undergo a color change within the buffer region. So what this means is that the acidic form is one color and the conjugate base form is a different color. The most common one that gets used is phenolphthalein. So the acidic form is colorless. The basic form is going to be a fairly bright pink. The location, or the way that you're going to select an acid-base indicator, is based on the pKa value for the indicator, often called the pKin for the acid dissociation constant for the indicator. This gives you a pretty good idea of the pH where the indicator is going to change color. So for phenolphthalein, the pKa for the acid of phenolphthalein is 9.5. This is the middle location of the buffer region for phenolphthalein. So the phenolphthalein would be normally doing a fairly slow transition between a colorless and a pink solution. But because we're using it as an indicator, the concentration of the indicators, they do have a slight effect on the titration. But what we're trying to do when we select an indicator is select something that has a very sharp color difference and is fairly bright. That way we can use the indicator at very low concentrations. If the concentration of the indicator is less than 1% of the concentration of the acid that you're analyzing, then the effect on your titration is going to be minimal, probably even negligible. So the reason that we often select phenolphthalein for a weak acid, strong base titration is generally the location on a titration curve where you have the greatest change is going to be in that 9.5 region, right? That's about where your equivalence point is going to be. And so because it's so steep in that region, that's going to be where your phenolphthalein changes color, making it so that the color change will happen near the equivalence point. When that occurs, we stop the titration and we call it the end point.